Okay, good morning, everyone. Welcome to this tutorial for META2021 from wherever you are in the world. Good morning from California. It's a nice, warm, sunny morning here in California, and I'm going to now begin my tutorial on design of active and reconfigurable metasurfaces. And so over the next hour, I'm going to say a little bit about the design aspects and the approaches to developing reconfigurable metasurfaces. They're shown here in this artist view of a reconfigurable active metasurface. And what you can see here is that this shows schematically an array of metasurface elements which are nominally identical in their geometrical design and their optical performance before they are actuated by a control electrode. So you can see each one is interconnected by a control electrode. And in so doing, they basically act as transformation elements on free space beams that enable us to control various aspects of the constitutive properties of light: the wave vector, the wavelength, the polarization state, the degree of beam focusing, and the wavefront. So I'm going to talk about all of those aspects over the next hour. So we'll begin. And first of all, I'll just note that the work that I will summarize today, much of the experimental and research work was done by a talented team of students and postdocs and former group members now at Caltech. And I'm going to describe principles for active metasurface design, the notion of so-called multifunctional tunable metasurface in what we call the quasi-static phase gradient modulation regime. I'm going to distinguish between quasi-static and time-modulated metasurfaces, and this distinction will be primarily over the frequency of modulation. When the frequency of modulation is such that the scattered or transformed light wavefront is substantially at the same wavelength as the incident beam, we'll call that quasi-static. And then we'll see that, in fact, there's another regime we can operate in, very much like the situation in RF metasurfaces and RF electronics, where we can, with very high frequency modulation, produce sidebands and enable multi-channel operation, which is an exciting new direction that's made possible by time modulation. So I'm going to describe aspects of active metasurfaces that are used for beam steering, dynamic focusing, and polarization conversion. I'll say a little bit about the different kinds of active media that we can use to generate the changes in complex permittivity that produce these changes in phase, amplitude, and polarization state. And I'll also note that metasurfaces, active metasurfaces, are made of real materials that have some non-ideal properties relative to our design objectives. And as a result, we can do inverse design optimization. That's, of course, a very familiar idea in nanophotonics at this point. But what we are going to see is that there's an opportunity to do array level optimization rather than essentially simply shape optimization of individual resonant or scattering elements. And then I'll get into the opportunities that are provided by time modulation of metasurfaces. So, okay, so our story begins, as all stories about metasurfaces, actually in the 17th century. So I just want to harken back to this towering figure of the Renaissance who provided the inspiration, the conceptual idea that provides the inspiration for all metasurfaces, which are in fact planar arrays of scatterers, where the scatterers produce outgoing, effectively spherical waves if they're small subwavelength scatterers, and the envelope of that's formed by the superposition of all those scattered waves defines the wavefront shape and the wave vector, and indeed we'll see also the frequency or the wavelength of the scattered light, and that of course, allows us then to use modern lithographic methods and print in a coplanar form these antennas, and we now have available to us concepts like this generalization of Snell's law that indicates a prescription for the scattered wave vector in terms of the phase gradient that's created by the superposition of the scattering elements that are located in this coplanar form factor. And of course, we have, with metasurfaces, we're able to design and create all sorts of transformations of light. We can, for example, create unusual and complex polarization states, for example, vortex beams, using a geometrical phase element as shown at the upper left in this slide. And in this case, we're taking arrays of antenna elements that are similar and simply changing their orientation in this geometrical or Pontcharrat-Berry phase concept to design structures that produce optical vortices. We can also, for example, couple between surface waves, like surface plasmon polaritons, or guided waves and free space waves using metasurface structures that are, in fact, polarization sensitive. So we can separate out, say, left and right circular polarization into waves that, when transformed into surface waves, propagate in different directions in the plane. We can use the gradient in metasurface phase and amplitude to form lenses that operate in reflection or transmission mode, as exemplified here by this Axicon lens. And these lenses have been successfully fabricated in frequencies ranging all the way across the visible. And in fact, a big push over the last few years in designing achromatic dielectric metasurface lenses. And of course, if we can encode phase and amplitude at will, then we have all the building blocks to encode holograms. And indeed, this is something that's been now practiced in a number of laboratories to demonstrate the capability for writing holograms, not only just using an object, but essentially a synthetically generated object, which creates the geometrical scattering and metasurface elements that produce that holographic image. So metasurfaces, of course, also have a very significant advantage over bulk optics, in the sense that not only are they flat and printable using lithography, they can encode multiple functions simultaneously. So, for example, this shows a concept that was introduced in similar time frame by the group of Andre Faro and my colleague here at Caltech and Federico Capasso, in which polarization sensitive antennas or metasurface elements were combined in a phase gradient array to allow for polarization as a mode of separating beams and focusing them separately at different focal lengths, for example, where rotation of the incident polarization allows the focal length to be adjusted. And all these are examples of what I will refer to as passive metasurfaces. So now we have to develop a new lexicon and talk about metasurfaces as not only passive, or not only metasurfaces, but passive and active, since we're going to introduce the concept of active metasurfaces. And the optical properties of passive metasurfaces are fixed at the time of fabrication. So I can rotate the polarization to create this difference in function, but I can't rotate the actual metasurface element itself. Tunable metasurfaces, on the other hand, enable post-fabrication modification of the function. So that's a very exciting concept, and it's the one that we're used to in many other forms in electronics and guided wave photonics. So as a result, active metasurfaces, from my perspective, have the very exciting prospect of yielding potential for future chip-based nanophotonics with greatly increased function and, relative to similar systems of similar function, decreased size, weight, and power. And broadly, my perspective on this is that the direction that we're going is building on the foundations of the beautiful solid-state technologies that preceded the metasurface era, which began roughly in 2010 or so, And those, of course, were these semiconductor electronic integrated circuits developed through the 1970s and 1990s. They kind of defined the way we think about solid state array technology, and this led to image sensors, memories, displays, and so forth. And then, of course, also in the 2000s, we saw the rise of photonic integrated circuits that were guided wave circuits. And a lot of this has really converged now to become a silicon photonics sort of technology, although there are other materials that are used for photonic integrated circuits like silicon nitride, even plasmonic integrated circuits in some specialized cases. And these essentially were forerunners to the metasurface optics revolution. And so we have now the opportunity to bring together, I think in the next 10 years or so, these beautiful foundational elements and very sophisticated technology from integrated circuit electronics and photonic integrated circuits together with metasurface optics that's taught us a lot about using this planar array of phase and polarization sensitive scatterers to control in real time the complex field and wavefront of the scattered light. So if you buy into that notion, then essentially that implies that active metasurfaces have the capability in principle for complete control of the constitutive properties of light, of radiation, where we could control the wave vector, the wavelength, the amplitude, the phase, and the polarization of light, either scattered light, which is what we're normally thinking about, but also we could design the elements on the planar array to be luminescent or to be thermally emitting or simply to be absorbing as ways to transform the transmitted and reflected beams, and to do this all as a function of time. And if we could do this, that would enable, in principle, a wide number of interesting applications that are emerging and people are excited about in the general sort of technology domain, including LiDAR as the essentially one of the sensor technologies that's needed for things like autonomous vehicles and, in fact, in portable devices for identification. And then, of course, Li-Fi, which promises to be essentially a means of very high bandwidth, short range wireless communications that is likely to supersede in some contexts the Wi-Fi technology that we now have. The opportunity to create projection displays of three-dimensional images, this is already sort of coming, but it's something that isn't really realized in a way that is compatible with the sort of platform that's shown here, a compact portable device. And finally, the metasurfaces that are being designed today, many of them are capable of high power operation. And if they're capable of high power operation, that implies a number of other possibilities in addition to imaging, including materials processing and additive manufacturing. So we think nowadays about additive manufacturing being something where we have a print head that thermally heats the material and then it deposits it at some voxel in 3D space. But we can also use optical beams to locally heat or photoexcite and transform materials to create 3D printed structures. And being able to access power densities in the, say, kilowatt per square centimeter range, I think will enable us to create active metasurfaces that are capable of doing things that are useful for additive manufacturing. So another important near-term application that's important to people that are interested in space technology is to replace the bulky RF apertures that are currently the mainstay of space communications. So for example, here you can see the size of the RF aperture on the Cassini spacecraft, and you can see that the RF aperture is comparable in size to the entire spacecraft. And that's because, of course, of the intrinsic limitations of the wavelength at RF frequencies. And it would be very desirable to replace this RF aperture with an optical aperture, an optical source and detector, simply because of the wavelength advantage of wavelengths, much smaller wavelength, and therefore the potential for a smaller aperture for communications. And that is an active effort that's being undertaken by NASA in the United States to develop, for example, this laser communication relay demonstration element here that's shown on the right. This, at the moment, is a structure that basically involves mounting conventional optics on mechanical gimbals and then simply mechanically manipulating and steering beams. Of course, what we'd like to do is to use metasurfaces which have the capability to be low profile and light with no moving parts, and which have demonstrated capability for sufficiently fast modulation speeds to create a phased array aperture at optical frequencies that could steer the beam and produce higher data rates and much more compact receivers. So, of course, also there exists in principle the possibility of having a much higher bandwidth as well as lower size weighted power. So this is an interesting application that may come out in the near term. And so if we think about quasi-static metasurfaces where the scattered wave is essentially the same as the incident carrier wave frequency at lambda incident, we could think about now creating, using reconfigurable antenna elements to create spatial phase gradients and amplitude gradients to and allow the phase profile to create the conditions to create an airy beam or to create a diffracted beam from an array of nominally speculatively reflecting elements before I applied the voltage. Here we have phase that alternates between arrays of antenna elements in a periodic array between 0 and pi. Or I could, for example, array the elements in terms of a phase gradient that is approximately linear as I go across the array of discrete elements in a repeating fashion, which would allow beam steering at a well-defined angle determined by the phase gradient. Or, for example, I could design a parabolic phase profile or some other phase profile which is matched so as to be able to produce a focused beam in front or behind the aperture. So we have at our disposal for active metasurfaces a number of the modulation mechanisms for altering the complex permittivity of materials. So one that I'll describe here as we go forward is via field effect modulation of the free carriers in a medium, semiconducting or conducting medium, and that therefore modifies the complex permittivity, which in turn modulates the amplitude and the phase. I could also use, for example, the same, many of you are probably watching this tutorial through a flat panel display device on your laptop. And the reconfigurable liquid crystal elements are transmitting colors at different wavelengths to your eye in a dense array. And that same sort of concept can be used to create phase gradient metasurfaces, particularly when coupled to high index dielectric structures. This is nice work that's been done by the group of Arseny Kuznetsov in Singapore in this regard. I could also use thermo-optic elements. This depicts a thermo-optic so-called optical phased array where waveguide phase shifters are coupled to antennas and then the light is coupled out in an array. It's not really a metasurface, but it illustrates the concept of thermo-optic phase shifting or modulation elements. I could make use of the electro-optic effect, which is applied across, for example, localized semiconductor quantum wells in 3,5 compound materials. This is the basis for the high-speed optical modulators that are used in modern communication systems. It's well known that they can operate in the tens of gigahertz range with fiber communication systems. And these same structures are effectively at optical frequencies in the C-band, telecom band. These are dielectric structures. They're not plasmonic, they're not metallic, they're all dielectric. And they operate by shifting the electronic wave function and changing the permittivity associated with confined electron hole pairs in the semiconductor quantum well. I could take advantage of materials that change their phase from amorphous to crystalline or from semi-metallic to semiconducting, as in the case of vanadium dioxide, or the chalcogenide glasses that have been used for optical memory kind of applications. And there are a number of researchers that have used this. And I could also design MEMS structures where, for example, I could create elements that are resonant optical structures that change their relative position and coupling to a mirror or to another optical element to modulate amplitude and phase. So I'll just mention a little bit about the all dielectric tunable metasurfaces before I spend some time on free carrier index modulation devices. And in this case, the reasons why we would be interested in such a metasurface technology are related to the fact that it's a structure that is all dielectric, in principle can be less lossy than structures that contain metallic elements, and could also enable both reflection and transmission. In other words, reflect array and transmit array modulation of the wavefront. Because there is no charge motion, it's essentially a capacitively excited device where I simply apply an electric field statically across a quantum well, has very high speed and low power consumption. There are existing foundry-based processes for designing quantum well header structures, which lowers the barrier to entry for people in the photonics field to use these materials. And by applying a voltage to a quantum well, what we do is we modulate the carrier distribution of electrons and holes in the quantum well. That modulates the complex permittivity at the band edge of the semiconductor. So this shows the band edge, the imaginary and the real part of the complex index of a indium gallium arsenide quantum well and gallium arsenide under at 0 volts and then also with an applied voltage. And what you can see is that there's a range in the wavelength range to the red of the band edge being right here, where you can see relatively large index modulation of the real part and quite small modulation of the imaginary part. This modulation of the real part is pretty small though, and so as a result, we have to build resonant structures to take advantage and produce significant phase shifts. And so we can combine the index modulation in quantum wells with resonant metasurface elements. Here's an example described in this Nature Communications paper, where Me resonant structures that have effectively a guided mode resonant structure on top. It's sort of a doubly resonant structure that supports a high order Me mode. That produces enough optical confinement and resonance to create a measurable phase shift in the range of about 70 to 90 degrees, and that enables the formation of a structure that exhibits switchable diffraction. And I think that's a very interesting direction to go for the future, particularly if we can produce higher Q structures that operate with all dielectric materials. And so semiconductor quantum wells are only one example of a dielectric material that you could use in this context. You could also think about using polarizable materials, things that, for example, piezoelectric or ferroelectric materials like barium lithium niobate or barium titanate as well. Another approach is to use the modulation of the free carrier index using a field effect channel. And essentially what we do is we form a metasurface antenna that in this, depicted here in a reflect array configuration, where this metasurface antenna also doubles as a field effect channel. This antenna has a confined mode that is highly confined within the gap between the antenna element and the ground plane. And this confined mode then has quite strong overlap with the material where the complex permittivity or complex index is being modulated. It's being modulated by an applied electric field between this antenna, which also doubles as a DC electrostatic gate to accumulate the carriers and deplete the carriers in this region. The other principle of operation that's important here is, and it's true for any active metasurface material, we want to align the region where there's a susceptibility resonance. In this case, we take advantage of the ENZ plasmonic resonance in a tunable material, where at ENZ, we're of course modulating the permittivity from slightly positive to 0 to slightly negative, from the dielectric to the plasmonic regime. And we want to modulate that in a regime that overlaps with the geometrical resonance of the antenna. In other words, if I didn't have this tunable element here, I could still produce an antenna that has a geometrical resonance at a wavelength determined by the design parameters of the antenna. But if I put these, I overlap these spectrally, then I can produce very strong phase modulation. And that phase modulation is the thing that makes possible the general general wavefront shaping that I described earlier. So this just describes the gate structure, the confinement. This shows an example of an array of one-dimensional array of metasurface elements. Within a material like ITO, indium tin oxide, an example of a transparent conducting oxide, it's a wide bandgap material with high carrier densities. We can adjust the carrier density of the material by chemical doping such that accumulation of carriers near the gate dielectric region, very similar to the principles of operation of a transistor, modulate the permittivity in this region between approximately +1 or 2 to -1 or 2 in this few nanometer region. And this is a region, of course, where the mode interacts very strongly with this tunable permittivity medium. So by now creating antenna elements where I can independently electrically connect to a large number of elements, in this case, this shows a chip that we've designed in our lab, where we connect independently to 96 different antenna elements. So that means we can apply 96 different voltage levels, or essentially to different voltages to 96 antenna elements. And that capability allows one to modulate the phase gradient among these nominally identical elements to enable beam steering, or for example, wavefront shaping to create a reconfigurable lens with a reconfigurable focal length and reflection. So the antenna elements that were used in this look like this. They have so-called fishbone geometry with a one-dimensional electrostatic interconnect here that goes off to the external circuit. The reflectance and phase are modulated as shown at the bottom, as we range in voltage between approximately -6 and 6 volts for this device. And that then creates a covariation of the phase and the amplitude. And you can say that if I started off and I wanted to design an ideal device, I'd want to simply smoothly vary the phase without varying the amplitude or the reflectance at all. And so this is a manifestation of the sort of non-ideal behavior. We have some loss. That loss gets greater near the ENZ resonance, and the reflectance goes down. And so there is some covariation. And I'll come back to that. That's a non-ideality, but it's not a disaster. It's something we can actually address with inverse design. So this illustrates the, if we simply were to apply, using a 4-level phase scheme here between 0, 90, 180, and 270 degrees relative to some reference phase, a linear phase gradient where I gang together and applied similar voltages to an array of adjacent elements so as to approximate, using this electrically activated array of antennas, linear phase gradient. So I can now adjust the slope of that phase gradient by changing the number of antennas that have identical phase levels in this 4-level phase scheme. And this, if I had perfect devices where I had no covariation of phase and amplitude, I would get highly directive beams coming out at these different angles corresponding to the different phase gradients depicted above. In experiments, what I find is I am able to steer a highly directed beam. There are also some undesirable artifacts where power is steered in sidebands that was not intended. For example, you can see there's some power steered at the specular beam position and a little bit of power off at negative angles here, whereas the steered beam is being steered at between about 9 and 21 degrees at positive angles. So I'll show how we can mitigate this with inverse design in a moment. So another thing that we can design is a reconfigurable meta lens. So meta lenses utilize the lens maker's equation to design a phase profile across the aperture that is a sort of wrapped phase profile, wrapped modulo 2 pi, to mimic the phase profile that's required for focusing. And so the simplest sort of prescription for a lens, assuming you don't have a lot of astigmatism, is a parabolic phase profile, and that's what this shows. And by applying voltages to an array of metasurface elements, we can electronically configure parabolic phase profiles with different parabolic radii of curvature here, and that therefore results in a tunable focal length for the scattered radiation, the reflected radiation, where the focal length is varying in this case between 1.5 and 3 microns. So that corresponds to, if you went to your optics lab and pulled out a microscope objective, that would correspond to a very high numerical aperture objective where you're focusing the light very close to the lens. And this illustrates here both the full field simulation and the experimentally measured focal point here, showing focusing very close to the lens. And of course, by opening up the curvature of this parabolic phase profile, I can now focus at greater distances, and this shows focusing out to about 25 microns, and we've been able to demonstrate focusing as far as 300 microns away from the metasurface aperture. So this is an example of a structure where I can now generate a lens with electronically tunable focal length, not by tuning the permittivity of some intervening medium, but by changing the properties of the metasurface itself. So active metasurfaces.
I think there's a question in the audience you want to quickly.
Okay, happy to field one if you want to go ahead.
Yeah, so I think it's related to the parabolic phase profile. So maybe I try to rephrase. So Poppy is asking about, do you have enough pixel actually creating this parabolic phase profile to get the reflection you want? And for example, how much pixel actually you may need to get a maybe better reflection you decide here?
Yeah, okay, that brings up a number of things related to design. So I'm glad whoever asked the question, I'm glad for the question, thank you. So one of the things to think about when you're designing any optical aperture is the size of the aperture relative to the wavelength itself. That will determine essentially, you'll have the finite size of an aperture will determine the transformation that can be created simply because of the diffraction limited performance of that aperture. In other words, if I were to focus a beam in the far field, I would have a focal length, which is also, if I had perfect devices and I had perfect metasurface elements and I could produce continuum phase gradients across the array, which I cannot do. If I could do that, then the ultimate limit to the focusing would be the diffraction limited size of the aperture. So then how big does the aperture need to be useful? For a wavelength of 1.5 microns, if you could go out to an aperture size of 1,000 wavelengths, say 1.5 millimeters, you would be able to focus very effectively in the far field. You would probably end up being limited by other aberrations in the lens, not the diffraction limit. So I would say, and that's certainly within the range of the chip-based technologies that I was talking about earlier. If you open up your iPhone or your laptop, you'll find a chip that is in fact centimeters in size. So clearly we can make electronically controlled apertures that big. So then another question would be, how many metasurface elements do you need? So if you had something that was 1,000 wavelengths wide, and we're using here subwavelength elements, slightly subwavelength elements to create a phase gradient continuum, that would be a couple thousand pixels, if you like, in the transverse direction over which the phase gradient is being created. In this case, we use just shy of 196. This shows that what I'm showing here are the data points for the discrete phases and the discrete voltages and phases applied to the metasurface elements. And so because we have subwavelength elements, the 96 elements span over a physical aperture size here of about 40 microns. You can see here it goes from plus 20 microns to minus 20 microns. So that's the size scale. So as I indicated earlier, this shows here the beam spot size that you would see as a result of the full field simulation from this finite aperture. And as you can see, that the experimental beam waste is not quite as good as the simulated, which is probably due to phase errors, random phase errors in the metasurface itself. But so that gives you an idea about some of the aspects of the design of the aperture.
Thank you. Yeah.
Okay. Okay, so with an active metasurface, we're using the bias voltage to create phase and amplitude variations among an element of arrays in an array. And as I mentioned earlier, we have this unavoidable and undesirable covariation of phase and amplitude in at least in materials that are lossy. Even in lossless materials, there will be, you'll see some aspects of this. And the phase modulation range is not from 0 to 2 pi completely. And that is in fact, and so you can see here, if I simply made a linear phase gradient, this would in fact, the dotted dashed line here indicates what the amplitude variation would look like given this device performance. This amplitude and phase versus voltage actually corresponds to a real TCO metasurface device. And so you can see here that this linear phase gradient, if it were an ideal device, would steer a beam at one angle. But you see here sidebands, undesirable sidebands, which lower the directivity of the beam. So one way to think about a metasurface, if the antennas are uncoupled, and despite the fact that they are densely arrayed, they are actually not strongly coupled to one another. So they're sub-wavelength in size and they're pretty closely spaced, but you can still get away with a very simple description to first order of the antenna field as being just the field comes from a scattered antenna plus an array factor. If there's inter-antenna coupling, things get complicated and you can't, this description breaks down, but in the limit where each independent antenna is an independent dipole scatterer, then you can use this array factor analysis to look at the steered beam in the far field. And so you can see here that as you produce linear phase gradients at different angles, you get undesirable side lobes. Okay, so what could you do about this? You could declare a design objective, and in this case, if you wanted to make a highly directive steered beam, the figure of merit would be the beam directivity. It would be the power in the central beam divided by the power scattered in all angles, including the undesirable side lobes. And then you would use an inverse design algorithm using this objective function to work backwards from your desired beam profile to give the array of antenna phase and amplitudes and voltages that would produce that, that desired profile. We happen to use in this work a genetic algorithm. You could use machine learning, generative adversarial networks, for example. That's another very efficient way of doing this. A number of inverse design optimization algorithms could be used. But to illustrate the point of array optimization here, I'll show you, this is the initial state here for an array of antennas that has approximately started out with an array. Here, let me back this up here to the beginning. Sorry, let me back this back up, where I have an approximately linear phase gradient that's repeated. And because of the covariation of phase and amplitude, has this very funny, complex, and not very intuitively understandable amplitude profile across the aperture. And it starts off with this array of far field scattering profiles, beam scattering profiles. So now I'll start covarying the phase and the amplitude. And as the iterative optimization goes on, what you'll see here, and there I'll look at the figure of merit function, which is the beam directivity value. You can see it iterates until, and it very quickly now is able to find a phase and amplitude profile. It's basically co-varying, co-optimizing the phase and the amplitude to produce a highly directive beam at this angle. And so you can see here, after a couple hundred iterations, it now saturates. The directivity isn't getting much bigger, but it's improved substantially relative to the quasi-linear. And you can see here, there is in fact a sort of recognizably quasi-linear phase profile, although you would not have intuitively in advance have guessed this particular phase profile to be the optimal one. So that illustrates the power of inverse design optimization. And here at the array level. So I'll move on and just show, here's an example showing how in the red, the optimized design enables directivity at different antenna repeat numbers corresponding to different scattering angles in the far field. And you can see that then suppresses the side lobes, which were initially present using a forward design approach. And so that's a way to overcome some of the non-idealities. And so intriguingly, one of the aspects of this is that you can compensate for one of the limitations of tunable permittivity media, which is that their phase modulation range doesn't extend over the entire range of 2 pi that you would think you would need to generate a phase modulated aperture to generate complete specification of the wavefront and the beam directivity. And you can see here, at least for this figure of merit for beam directivity, that I still can obtain pretty high directivity even with a phase modulation range as small as pi, half of the fundamental limit of 2 pi. So I can still, even if I have a quite non-ideal structure, use inverse design to achieve this. So this was a bit of a surprise to us, and I think this is pretty encouraging for use of real materials and real devices in active metasurfaces. You could also, for example, build devices that have dual gates. For example, this is very much like a dual gated transistor in which you apply a voltage between the body of the device and the gate, and the body and the device and the substrate, or in our case, the reflective ground plane. The result of that is that you get 2 regions where the free carrier index is modulated, one right under the gate and one right at the back surface of this device. And that allows you to have much more design freedom in changing the phase and amplitude. Now, they both co-vary when you do this, but you can find, for example, here's a range where the phase modulates rapidly, the reflectance modulates slowly. So it gives you another design degree of freedom. I want to also call out attention here to a nice new result from my friend and colleague Jung-Young Park from Samsung Advanced Institute of Technology, who utilized this concept that we talked about a couple of years ago to produce metasurfaces where he was able to match the complex admittance or complex impedance across the array of voltages to enable this device to achieve 2 pi phase modulation, even though it has covariation of phase and amplitude. So that's nicely described in this paper. And his group also in this paper showed a, well, first sort of semi-practical LiDAR demonstration here, showing a metasurface, reflector array metasurface here with an image sensor co-located with the metasurface aperture here, and it's able to discriminate, as you can see in this image, between the object in the far field and in the foreground, sort of a notional pedestrian standing in front of the vehicle. So that illustrates the kind of structures that the way these metasurfaces can work. So I wanted to here just describe and note that the TCO-based metasurfaces do have some undesirable features related to the losses of the material. And you can see that the ITO material here off resonance, where I'm far away from the ENZ resonance, is not the major contributor to the absorbance of the device. Here I've separated the absorbance of the different device elements into the antenna backplane and the active medium. And you can see at resonance, the active medium dominates the overall absorbance and loss in the device. So I could, in fact, mitigate this by going to a better material. I could use a material that has a higher mobility. And it's well known that one of the materials that has higher mobility than the typical transparent conducting oxides is cadmium oxide. And I think with this, and you can see here that the absorbance is still pretty high, but nonetheless sufficiently lower to be quite useful as an alternative to the other known conducting oxides. So I think this illustrates the power of materials design to improve the performance. And we've done some analysis. This will be published in a forthcoming paper shortly, comparing the characteristics of these TCO-based metasurfaces with all of their current state of development and non-ideality for applications like LiDAR and free space optical communications. And we looked at the analysis in the limit where we had both CW and pulsed excitation from a source impinging on the metasurface aperture. Beam here, diameter of 2 millimeters, so corresponding to a 2 millimeter size aperture, and a receiving detector of 3 centimeters sitting on the other end, and a CW beam of about 100 watts, and corresponding to an irradiance of 3 kilowatts per square centimeter. We've also been able to show that metasurfaces are tolerant of such power densities, and pulse beams here with nanosecond pulses that correspond to about 100 millijoules pulse energy. So these are all typical values. And what you can see here is that this implies that we could use even the metasurfaces we have today for ranges at CW over the range of a few hundred to 1,000 meters, or even kilometers, many tens of kilometers in pulsed regime for things like LiDAR. And in space where we have no intervening scattering elements, we could think about using where the signal to noise is determined by the signal to noise properties of the receiver, ranges over hundreds of kilometers at CW to tens of thousands to hundreds of thousands of kilometers using pulsed technology. So this is really quite interesting. Okay, I want to now quickly finish and then maybe have some time for questions. I just mentioned that we can use the complex phase profile to steer multiple beams in multiple directions. We can tune polarization too. We can configure metasurface elements where the resonance along the transverse and longitudinal directions allows for linear X to linear Y cross polarization conversion, or linear to circular polarization conversion, so essentially making an electronically tunable quarter wave plate or half wave plate. I'm going to skip some of the details of how this operates. It's described in this new paper in Advanced Optical Materials. But the result of this is that by tuning the voltage, one can develop the prescription for accessing a large range of trajectories on the Poincare sphere, going from linear polarization along the equator to circular polarization at the pole. I want to also mention another really exciting new development, and this is not yet published, but I can't resist telling you about it, and it's forthcoming soon, is that we can use the properties, interesting properties of new materials, and this illustrates the new material black phosphorus. Black phosphorus is a material that has an anisotropic permittivity, and its anisotropic permittivity is voltage tunable. Its permittivity changes along the armchair direction of the layered van der Waals material, but not along the zigzag direction. And that means that when I create a little gated heterostructure that also acts as a low Q optical cavity, I can now tune the permittivity along the armchair direction so as to traverse trajectories along the Poincare sphere that correspond to quarter wave plate and half wave plate operation. And so this takes advantage of the change in the real part of the refractive index across the telecommunications band and the imaginary part in black phosphorus. Black phosphorus is a sort of naturally occurring quantum well. In a way you could think about it, this is a quantum well electro-optic modulator. And by designing your heterostructure appropriately, this is a little Fabry-Perot cavity, you can now create trajectories, complex permittivity trajectories along the armchair and zigzag direction in the complex permittivity plane, which allow us to modulate phase and amplitude along the two directions differently. Now I can create cavities that are resonant at different frequencies across the C band in the telecommunication regime. I can actually span all of these bands, the E band, the S band, and the C band, by changing the cavity length. And I can also traverse different trajectories on the Poincare sphere. So this is really quite interesting. This is now telling us that we have the elements of building an electronically tunable polarimeter using metasurface elements. And this shows here the tunable polarization here, this shows for a given frequency for a given cavity structure, the profile of the scattered beam here in terms of its ellipticity, and you can see here, this is operating as a quarter wave plate going from approximately linear to circular polarization at this voltage state. This is data and here a half wave plate where you can see the polarization rotation as a function of the applied voltage. So I think really look forward to the introduction of new materials. So finally, I'll say a few words about time-modulated metasurfaces. This is just a field that's beginning. And just as we can create spatial phase gradients that create beams that are steered at certain angles, we can create temporal phase gradients where beams are steered at well-defined frequencies relative to the incident optical carrier frequency. I'm going to skip some of the work on the RF analogs. You probably know that we can build RF phased arrays and RF sideband generation elements. This is exactly how FM radio works. And this just illustrates the different waveforms we can use. We can create a single sideband or a dual sideband structure by changing the temporal waveform, in this case, that's applied to a metasurface element. And what we do is apply using either an arbitrary waveform generator or an arbitrary waveform generator coupled together with phase shifters to change the temporal phase profile that's applied and the relative phase temporal position to arrays of adjacent antennas. And we can create, therefore, temporal gratings, temporal 2-level and 4-level gratings that allow for the possibility of multi-frequency and multi-beam scanning. So, by the way, what is the shift in wavelength? It's actually pretty small. It's of the order of picometers, but the criteria for the wavelength shift that we need is determined by the laser line width. And laser line width of modern lasers is sub-megahertz. So that means that if we have modulation frequencies in the megahertz to gigahertz range, that's really what is required to produce an array of sidebands and essentially multiplex the channels that are available for communications. So these metasurfaces that have an ideal metasurface would have some smoothly varying phase with applied bias and no change in amplitude, and would produce a single harmonic at a given frequency. If I have real materials, they have covariation of phase and amplitude. I need to use a more complex temporal profile, temporal waveform. I can still get a predominant sideband, even though I have some smearing out of power at other frequencies. So this illustrates how you do these kinds of measurements with a active metasurface that's driven by an arbitrary waveform generator. And so we look at so this is in the lab. I will go through and we can create structures. This is using a test element with an acousto-optic modulator showing that we can create frequency spectrum using these different waveforms. So as a sort of a warm-up test. And we're now currently working to develop temporally modulated waveform structures on diffractive metasurfaces and metasurfaces that have independent elements that allow for essentially steering of by controlling the phase gradients at different different frequencies and different temporal waveforms to create different spatial waveforms, so we can steer different frequencies at different angles in a somewhat more arbitrary form. So I'll stop here and be happy to field some questions related to my talk.
Okay, thank you, Harry, for the really exciting tutorial talk. And if you have any question, please type in the chat box or the question and answer box, and we can ask for you. And first of all, also apologize. I thought this session is chaired by Iswa Agawa, but he's not here, so you are not properly introduced at the beginning. But thank you for the nice talk. So I think there are a couple of questions here. So first question will be, in your electrical device, there are a lot of electrical contact. So is that a major problem? And if there any solution to make actually a smaller number of contact to the metasurface?
Yeah, Okay, so that's a really good question. So this is one that looks pretty forbidding. And I also want to give a shout out to my former student, Ghazala Cafe-Shurmanesh, who produced this device with 96 different elements. That was quite an effort for a university-based project. What I should say, though, is that in industry, industrial chip designers routinely build chips with hundreds of pinouts, even thousands. If you open up and look at your microprocessor in your laptop, you'll see that the chip package has many, many interconnects. Furthermore, there is a serialization and deserialization element, usually with an A to D converter, that allows one to do bit line, word line addressing to address individual pixels. This is not something that university people typically do unless they happen to be circuit design people that fab their chips through foundries like TSMC or Moses. You typically don't build them in your own university clean room because they're sufficiently complex, but you can make chips, and these are being designed by some of the early stage companies in this area, where you use bit line, word line addressing to address individual pixels in an array. In some cases, you can actually, what I described here were arrays that were 1D arrays, in the sense that the phase modulation or phase gradients are in one spatial dimension. In LiDAR, some of the early LiDAR devices are based, if you think about LiDAR, you're steering a beam near the horizon. You don't need to steer a beam up in the air because the oncoming traffic isn't coming out of the sky, at least not yet. And so 1D phase gradient modulation may actually be sufficient to be useful in LiDAR. But to make chips that have interconnects in 2 dimensions, we need to have a addressing technology. But this already exists for displays, memories, high-speed logic chips. So that would be, I think, my outlook for the future of this. So it may require people in industry working on this.
So it's a little bit hard for the university to completely making a actual device, 1,000 contact probably.
Well, and I would say that at some point you need to go walk down the hall to your circuit design colleagues who do this every day. So many of us in the nanophotonics community don't live in that world. And so we need to go talk to people that do, but there are people that do this all the time that design project chips with very complex circuit designs.
That's right. Okay. Yeah, there's another question. So for the beam steering device using the ITO layer, in order to get the phase modulation from the 0 to 2 pi, is it important to use both the electric and magnetic dipole resonance of the Leno antenna?
Okay, that's interesting. Good question. So effectively, I would say the most important criterion is to be able to have access, whatever mode you're using. In fact, the modes that, the optical modes that were used in the devices that I showed were identifiably as primarily magnetic dipole resonances. So the key prescription, I showed this, maybe I'll go back and share the slides again for a minute. The key prescription to do this is to be able to access the entire, let's see here, I wanted to show this result from Jungian Park here. Let me see if I can find this. Yeah, here it is. So the most important key aspect of this, I think, is to be able to control, to find the, to be able to span the entire complex plane. So here we're looking at the real and the imaginary part of the complex reflection coefficient. You want to be able to span over this entire angular range in the complex plane. So that actually can, I think, be achieved primarily by changing the medium and the way it overlaps with a given mode, namely the magnetic dipole mode, rather than using a hybridized mode. I have to think about that. Actually, it's kind of an interesting suggestion. If you're using higher order modes, it may open up some degrees of freedom where you might hop from one mode to another. But these devices are operating in a single mode regime.
Okay, thank you. And actually, I personally have another question. So far, it's really difficult for the metasurface community to even making a large area metasurface. So how about a tunable metasurface in large area? What is your perspective? And I think there's certainly certain application will need a large area, but what is your perspective on making a large area tunable metasurface?
Well, there are already underway several efforts around the world on this. And as I said, it requires help from our friends on the circuit design side and on the fab side. But it's going to happen. I can tell you that there is several efforts underway. Some of them are not academically based. Some of them are based in companies. But large area devices are definitely, in fact, they've already been demonstrated. If you, I'll draw your attention to the work of a company, an early stage company called Lumotive, that has been able to design active LiDAR type devices using quite large area apertures.
Mm-hmm. Okay, sounds great. And there's another question, a little bit long. So regarding the parabolic phase profile, you have a central parabolic parabola, and then you have a bench that repeat themselves periodically in the left and right of the center of parabola.
Right.
And those actually repeating bands so that you can get a parallelistic reflection from them.
Yeah, I mean, this is just the prescription from the lens maker's equation. So, for example, if you think about a reflective specular reflecting mirror, if I wanted to create a lens with a mirror, I would actually physically shape it as a parabola. Like you can buy such things from Edmund Optics and things like that. However, I could also make a lens where the phase profile is wrapped modulo 2 pi. And a good example of that is a Fresnel lens. And so in essence, this is simply a wrapped phase profile where the phase is wrapped modulo 2 pi. So if you were to unwrap this phase profile, it would look essentially like a parabola.
Mm-hmm. Okay, sounds great. And so if any of you have more questions, please type in the question and answer boxes. So I have another question regarding the phosphorus. So it's really interesting. You can tune the polarizations. So is that a really thin layer of that? And also what will be the efficiency of some of those polarization?
Yes, okay. It is very thin. It's exactly 3 layers thin.
Okay.
So by the way, the reason it's 3 layers is because black phosphorus is as I mentioned, it's a natural quantum well. As you know, a quantum well has its subband absorption wavelengths are determined by the thickness of the quantum well. That's true for all quantum wells. And black phosphorus is a naturally occurring quantum well, so it will have effectively different subband or band edges for monolayer, bilayer, trilayer, and then bulk black phosphorus. So it is a semiconductor whose band gap is tunable with thickness because it's effectively a quantum well. So if I want to operate in the telecommunications band, the C band and the S band and so forth, then it turns out that the thickness that I need is 3 layers. And in terms of the reflectance, you can see here, let me, you can see we have quite large reflectance and reflectance modulation. The actual structure here is a very simple cavity scheme. It's just using here black phosphorus with a semi-transparent mirror, gold mirror. It's a very simple cavity. So you can see here what the reflectivities are as they vary across the. So the reflectivity does drop near the resonance, but there is reflectivities of tens of % near the resonance. and a large portion of this, if you wanted to make a more higher reflectivity device, you could replace these gold mirrors with for example, dielectric mirrors.
Okay, sounds great. There's another question regarding, do you think the voltage value lookup for each metasurface element will not be too computationally expensive? I think it's referring to the inverse design.
Inverse design, okay, yeah.
That's right.
So I would say that the powers of inverse design are being very widely demonstrated in the nanophotonics community. And okay, I guess there are two ways to think about doing inverse design. There's one way, which is the way I described, which is to use an algorithm and to compute it using this algorithm beforehand. There's another way to do inverse design, which is to simply use an imaging detector, which can, for example, detect the profile of your beam, and simply to iteratively optimize in analog fashion the voltages applied in the laboratory to your device until you reach an optimum. That's sort of an empirical way of doing it. But I would say that the computational burden is not overwhelming for this kind of structure. As long as you start out with the knowledge of the relationship between the voltage, phase, amplitude, and polarization state, you can use that as a lookup table in your design. So we don't recompute, and by the way, we're not computing full field simulations in each iterative step because we're using this array factor model. That, by the way, can run on your iPhone. That's very computationally compact.
Okay, thank you. And there's another question. Can you briefly mention about the application in the RF regime? Are there any particular advantage or challenge when working in the band of RF modulation?
Yeah, so that's a good question. And in fact, this meeting, META, is kind of a communion of people that work in the RF and in the optical regime, and sometimes they don't always talk to one another. RF circuit designers know that the careful design of the impedance of interconnects and so forth is very important to avoid RF dispersion and losses. So one of the things you have to think about when you're designing the interconnects to a tunable metasurface that operates in the RF regime is about those impedance matching considerations. It's the same sort of thing I would think about if I were designing a high-speed telecommunications modulator. Turns out that a lot of that involves very sophisticated RF design to apply the voltages at high frequencies. But that's a known a body of knowledge on how to do that and create RF modulation at tens of gigahertz.
Okay, that's great. Yeah, I think that's all the question I can see. And probably let me thank you, Harry, again for the great tutorial talk, and thanks a lot and all your attendance as well. Okay. And I hope to see you in the next 2 days as well in the Meta conference. So thank you very much.
Okay.
See you. Bye.
Bye, everybody.